Hello, dear students. Today, we will be dealing with first, solution of a system of linear inequality in two variables. Second, graphing a system of linear inequality in two variables. And third, solve problems involving linear inequality in two variables. These were taken from the module titled Systems of Linear Inequalities in Two Variables by Joyce B. Jimenez. At the end of the lesson, you are expected to demonstrate understanding of how to graph a system of linear inequalities in two variables, solve problems involving system of linear inequalities in two variables, and determine if an ordered pair is a solution of a system of linear inequality. Always remember, in graphing the boundary line or the plane divider, use broken line for the greater than and less than symbols, and solid line for greater than or equal to and less than or equal to symbols. And to decide which side of the boundary line to shade, get a test point that is not on the boundary line. If the test point satisfies the inequality, then shade the half plane where it is located. Otherwise, shade the other half plane. So now I think we are already ready to proceed to our today's lesson. Let us now have lesson 1. Solution of a system of linear inequality in two variables. But before that, what do we mean when we say system of linear inequalities in two variables? So it consists of at least two linear inequalities in the same variables. Some of the examples are as follows. First, we have the system 6x plus 3y is less than or equal to 12 and 3x minus y is less than negative 6. So observe that there are two linear inequalities with two same variables, x and y. Another example is x plus y is greater than 3 and x minus y is less than 3. Another one, x plus y is greater than or equal to 4 and y minus x is greater than or equal to 2. And we may also have three linear inequalities. We have here 5x is greater than y, 2y is less than x, and 2x minus 5y is greater than or equal to 0. Let us have now the solution of a system of linear inequalities in two variables. Its solution is an ordered pair xy that satisfies both or all inequalities in the system. So like systems of linear equation and linear inequalities, the solution also of a system of linear inequalities are all ordered pairs that satisfies all the given inequalities. Let us have examples. So what we're going to do is to determine if the given ordered pair is a solution of the system or not. First, 6x plus 3y is less than or equal to 12 and 3x minus y is less than negative 6. And what we're going to test is the point negative 3, 5. So to do that, we simply have to substitute negative 3 to x and 5 to y. So using the first inequality first, we have 6x plus 3y is less than or equal to 12. Then by substitution, we now have 6 times negative 3 plus 3 times 5 is less than or equal to 12. Simplifying the inequality, we now have negative 18. That's from 6 times negative 3. And from 3 times 5, we have 15. And adding negative 18 and 15, we have negative 3. So we have here now negative 3 is less than or equal to 12. Next is negative 3 less than or equal to 12, a true or a false statement. So since the inequality symbol pointed to the negative sign or to the negative number, then that statement is true. Next, we will use now the second inequality. 3x minus y is less than negative 6. Again, by substitution, we have 3 times the value of x, which is negative 3, minus the value of y, which is 5. That's less than negative 6. Multiplying 3 by negative 3, we have negative 9 minus 5. Simplifying negative 9 minus 5, that's negative 14. So we have here negative 14 is less than negative 6. Is that a true or a false statement? So obviously, it is true. Since both or since the given ordered pair is true to both the two linear inequalities, then that point is a solution of the given system of linear inequalities. Let's have the second example. X plus y is greater than 3 and x minus y is less than 3. So first, we have to test the given point using the first linear inequality, x plus y is greater than 3. By substitution, we have negative 2 plus negative 3 is greater than 3. Negative 2 minus 3, that's negative 5, is greater than 3. Now, is negative 5 greater than 3 a true or a false statement? Of course, it's a false statement. Now, since we arrived at a false statement, that means we can now conclude that the given point does not satisfy the given system of linear inequalities. Next, we have the third example. X plus y is less than or equal to 4 and y minus x is greater than or equal to 2. Let us test the point 8, 3. Is it a solution of the given system of linear inequalities? So again, we have to substitute using the first linear inequality, x plus y is less than or equal to 4. We have now 8 plus 3 is greater than or equal to 4. 8 plus 3 is 11. So we have 11 is less than or equal to 4. And that statement, of course, is false because 11 is greater than 4. Again, since it's a false statement, you can now conclude that the given ordered pair does not satisfy the given system of linear inequality. Let us try to test the second inequality. Y minus x is greater than or equal to 2. By substitution, we have 3 minus 8 is greater than or equal to 2. 3 minus 8 is negative 5 is greater than or equal to 2. A positive number is always greater than a negative number. Therefore, that statement is false. The given ordered pair does not satisfy both the given linear inequalities. Therefore, the the ordered pair does not satisfy the given system of linear inequalities. We now have lesson 2, graphing systems of linear inequalities into variables. So to graph a system of linear inequalities in two variables, remember the following steps. First, graph the individual inequalities on the same coordinate axis. Second, determine the intersection of the graphs of the inequalities or the region where the graph overlap or the double shaded region. And last, pick a test point for the region to verify the solution. Following those steps, let us have examples. First, graph the system of inequalities y is greater than x minus 2 and y is less than 2x plus 2. Step 1. So we're going to rewrite the linear inequality as an equation. So we have to change the inequality symbols to equal sign. So we now have y equals x minus 2 and y equals 2x plus 2. Next, we have to determine the x-intercepts and y-intercepts of the two given equations. Using the first equation, we have y equals x minus 2. To get the x-intercept, we have to set y equals 0. So we have 0 equals x minus 2. That means x equals 2. For the y-intercept, we have y is equal to 0 minus 2. Therefore, y equals negative 2. So the x-intercept is 2. In the x-axis, 2 is here. So this is x equals 2. And on the y-axis, we have here the point negative 2. Now connecting x equals 2 and y equals negative 2, we now have this line. Take note, since the given inequality symbol is greater than, we're going to use a broken line for the boundary line. For the second inequality, y is less than or equal to 2x plus 2. That is now y equals 2x plus 2. Then solving for the x and y intercepts, we have x equals negative 1 and y equals 2 by substitution. So we have x equals negative 1. Negative 1 is here on the x-axis. And y equals 2, it's above 0 on the y-axis. So connecting those 2 points, we have here a solid line because the given inequality symbol is greater than or equal to. So we now have this boundary line. Step 2. We now have to determine the shaded region. And that is done by testing the point 0, 0. By substituting x and y with 0. So using the first linear inequality, y is greater than x minus 2. We have 0 is greater than negative 2. That statement is true. So from the graph, Since, take note, this is our first boundary line. And we tested 0, 0. It's here. And since it is true to the origin, then we're going to shade the upper part of the boundary line or the upper region of the boundary line. Therefore, this is the region where y is greater than x minus 2 is located. And then, using the second linear inequality, y is greater than or equal to 2x plus 2, and substituting 0, 0, we have 0 is less than or equal to 2 times 0 plus 2. Therefore, 0 is less than or equal to 2. And of course, that statement is true. Therefore, again, considering the second boundary line and the testing point 0, 0, we have to shade the region where that 0, 0 is found. So that is the right side of the boundary line. So the shaded region is here. That means y is less than or equal to 2x plus 2 is found on this region. As what we have said a while back, the solution of a system of linear inequalities in two variables is the intersection of the graphs of the inequalities or the region where the graph overlap, or it's the double shaded region. So since this is the graph of the first inequality and this is the graph of the second inequality and they overlap at this point, that's why this is a double shaded region. Therefore, the solution of the given system of linear inequality is at this region. So all the points that are found on this region are all solutions of the given system of linear inequalities. Next, step 3. We now have to pick a test point for the region to verify the solution. This is already the checking part, testing whether our answer is true. So we have here the points A, B, C, and D, which are on the graph. A, we have negative 1, 1, C, 2, negative 4, D, negative 6, negative 9, B, 3, 2. For A, we have a true and a false statement. That means A does not satisfy the given system. For C, we have one false and one true. So like A, this point does not satisfy the given system. For point D, we have two false statements. So obviously, this point does not satisfy the given system. And for point B, we have 3, 2. Note that both statements are true. Therefore, the double shaded region here, including the solid boundary line, is the solution set of the given system of linear inequalities. Let us have another example. Show the solution set of the system of linear inequalities. X is less than or equal to 3 and y is less than or equal to 2. Step 1. Again, we have to rewrite the linear inequality into an equation. So, changing x is less than or equal to 3, we now have x equals 3. And then from y is less than or equal to 2, we have y equals 2. Note that since the given equation is x equals 3, that means it's a vertical line. For y equals 2, it's a horizontal line. because whatever value of x is, the line is still at y equals 2. Next, considering the given inequality symbol, since we have 2 less than or equal to, then both boundary lines are solid lines. So we have here x equals 3. It's a vertical line, and on the x-axis, we have 3 here. So we have a vertical line passing through x equals 3. Passing through the x-axis at point 3. And then for the second inequality, y is greater than or equal to 2, we have here a horizontal line passing through the y-axis at point 2. Next step, we have to determine now the shaded region. That is done by testing the point 0, 0. By substitution, we have 0 is less than or equal to 3 and 0 is less than or equal to 2, which are obviously both true statements. Therefore, the shaded region should be the region where the point 0, 0 is found. So on the graph, for x is less than or equal to 3, we have to shade the point where 0, 0 is found. So that means the shaded region is on the left side of the boundary line. So this is where x is less than or equal to 3 is found. And for the second inequality, y is less than or equal to 2, considering point 0, 0, which should be on the solution of the given inequality. So we have to shade the lower region of the boundary line. That means this region is for y is greater than or equal to 2. And of course, the region where those two graphs overlap, that is the solution set of the given system of linear inequality in two variables. Therefore, again, all the points that are found on this region, including the point where those two boundary lines are found, are all solutions of the given system of linear inequalities. Third step, we now have to pick a test point for the region to verify the solution. Using -3, -2, we have this point. If we arrive at a true statement to both linear inequalities, then our answer or our solution set is correct. So by substitution, we have x is less than or equal to 3. That is -3 is less than or equal to 3. And of course, that statement is true. For the second inequality, we have y is less than or equal to 2. So we have -2 is less than or equal to 2. So obviously, that statement is another true statement. So since both statements are true, then that means the solution set of the given system of linear inequalities shown on the graph is true. Next example, we have to graph the solution of the system -3x plus 2y is greater than 6 and 6x minus 4y is greater than 8. First step, We have to rewrite the linear inequalities as an equation. We have to rewrite the linear we ha- we have to rewrite the linear inequalities into equations. So we have to change the given inequality symbol greater than to an equal sign. Next, since we already have here two equations, we are now ready to find their intercepts. So by substitution, for the x-intercept, we have to let y equals 0. That is negative 3x plus 2 times 0 equals 6. Therefore, we have negative 3x equals 6. And dividing both sides by negative 3, we have x equals negative 2. For the y-intercept, we have to let x equals 0. So by substitution, we have negative 3 times 0 plus 2y equals 6. So 2y equals 6. And dividing both sides by 2, we have y equals 3. For the second inequality, we have to find the x-intercept by letting y equals 0, that's 6x minus 4 times 0 equals 8. Simplifying, we have 6x equals 8. Then dividing both sides by 6, we have x equals 1 and 1/3. For the y-intercept, we have to let x equals 0. So we have 6 times 0 minus 4y equals 8. Negative 4y equals 8 and dividing both sides by negative 4. So we have y equals negative 2. Since we have the same given linear inequalities and that is greater than, then both inequality will use a broken line. So we have this graph for x equals negative 2, it's here, and y equals 3, we have this one. Connecting those 2 points or 2 intercepts, this is now the graph of or the boundary line of the first inequality, negative 3x plus 2y is greater than 6. For the second inequality, we have x equals 1 and 1/3. 1 and 1/3, it's here. And y equals negative 2 is below 0. So connecting those 2 points, this is now the graph of the second linear inequality. Step 2. We now have to determine the shaded region. That is by testing the point 0, 0 by substituting x and y with 0. So we have here negative 3x plus 2y is greater than 6. By substitution, we have negative 3 times 0 plus 2 times 0 is greater than 6. Simplifying the left side of the inequality, we now have 0 is greater than 6, which is obviously a false statement. And for the other inequality, we have 6x minus 4y is greater than 8. So we have 0 minus 0. So we have 6 times 0, that's 0. Minus 4 times 0 is 0. So 0 minus 0 is 0. Is greater than 8. Again, it's a false statement. So shading the region where the point 0, 0 is not included, we now have here the graph of the given two linear inequalities. So for negative 3x plus 2y is greater than 6, we have this line. So since point 0, 0 is not included on that graph, or on its graph, then the shaded region is at the upper left side of the boundary line. So it's at this region. And for the second inequality, 6x minus 4y is greater than 8. Since 0, 0 is not included, then the shaded region is at this part. So as you can see on the graph, we do not have here an overlapping graphs, or we do not have here a double shaded region. That means there is no solution. That means the given system of linear inequalities has no solution. And that ends our discussion for the second lesson. Let's now proceed to our third lesson, problems involving system of linear inequalities in two variables by graphing and by using the solution of the system of two variables. First example. Mrs. Burgos decided to sell her plants for additional earnings this pandemic, so she buys soil and pots for her to use in her planting her plants. The soil cost 200 pesos per sack and the pots cost 20 pesos each. How many pieces of pots with at least 2 sacks of soil can she buy if the total cost is not to exceed 1,000 pesos? So first, we have to represent the unknown variables. Let x be the number of pots and y be the number of sacks of soil. Now, since we have represented the unknown variables, we can now write the inequalities. So, since from the given, it was stated that the soil costs 200 pesos per sack and the pots cost 20 pesos each, and the total cost should not exceed 1,000 pesos. So we have the linear inequality, 20 times the number of pots, that's 20x, plus 200, the cost of soil per sack, times the number of sacks. So we have y. Since the term used is not to exceed, so we have less than or equal to 1,000. So that's the first linear inequality. Since the problem asks for the number of pieces of pots that she can buy with at least 2 sacks of soil, then we have the number of sacks of soil should be at least. So that's greater than or equal to 2 sacks or 2. So we have y is greater than or equal to 2. Graphing those two linear inequalities, we have this one. This is y is greater than or equal to 2 and the 20x plus 200y is less than or equal to 1,000 is on this graph. The shaded region here is this part, and for y is greater than or equal to, we have this part. So the shaded region or the double shade double shaded region is on this part. So all the points or all values that are on this graph are all solutions of the linear inequality. So say for example, we have like this point, we have 10 for x, that means she can buy 10 pots and 3 sacks of oil. Or she can also buy 5 pots and 4 sacks of oil. Or she can also have 25 pots and 2 sacks of oil. Another example, Jason needs to buy fruits. A mango costs 20 pesos each, while guava costs 15 pesos each. He can only spend at most 180 pesos and the total number of fruits is not more than 8. Can he buy A. 7 mangoes and 3 guavas? B. 6 mangoes and 4 guavas? So to answer those questions, we have to represent first and find for the system of linear inequalities applicable to the given problem. So if we let x to be the number of mangoes and y to be the number of guavas, we have the inequalities 20x plus 15y is greater than or equal to 180. So that means the cost of mango, so that's 20 times the number of mangoes, plus the cost of guava, that's 15 times the number of guavas, is less than or equal to, because we have at most 118. So that's our first linear inequality. And for our second linear inequality, we have x plus y is less than or equal to 8, since it was stated that the total number of fruits is not more than 8. Not more than means less than or equal to 8. So to find the answer for those two questions, we simply have to substitute the number of mangoes and number of guavas to x and y. So for A, we have 20 times 7 plus 15 times 3. Is that less than or equal to 180? So let us see. 20 times 7 is 140, plus 15 times 3 is 45. Again, 140 and 145. Adding those two numbers, we have 185. Now, since 185 is not less than or equal to 180, then that means the answer here is no. And also, if we try to substitute 7 and 3 to the second inequality, x plus y is less than or equal to 8. We have 7 plus 3, that's 10, is less than to or equal to 8. Again, that question is no to the second linear inequality. Next, can he buy 6 mangoes and 4 guavas? So again, by substitution, we have 20 times 6, that's 120, plus 15 times 4, that's 60. 120 plus 60 is 180. So that question is true to the first linear inequality because we have 180 is less than or equal to 180. Now for the second linear inequality, we have 6 plus 4 by substitution. That's 10 is less than or equal to 8. Since 10 is not less than or equal to 8, then that means the answer for that question is another no. So before we end, always remember that a system of linear inequalities in two variables consists of at least two linear inequalities in the same variables. and its solution is an ordered pair xy that satisfies both or all inequalities in the given system. And for graphing system of linear inequalities in two variables, we simply have to follow these steps. First, graph the individual inequalities on the same coordinate axis. Second, determine the intersection of the graphs of the inequalities or the region where the graph overlap, or the double shaded region, because that is where the solution of the system of linear inequalities is found. And last step, pick a test point for the region to verify your solution. And of course, for solving problems involving systems of linear inequalities in two variables, first, you have to represent the unknown variables and find the system of linear inequalities. And find the system of linear inequalities, you will need to solve the problem. Then after that, you solve the system of linear inequalities by graphing or by substitution. And last step, you have to, of course, write the conclusion or answer now the question on the given problem. That's all, and that ends this video lesson. Thank you all for watching.